In section 9.5, we're going to look at total differentials and then approximations. So let's start with a total differential. We can have either 2 or 3 variables. So our term here is we're going to use dz, and to find it, we're going to take the partial at x times dx, and then we're going to add the partial at y times dy. So similarly, if it's 3 variables, we'll have the partial at x times dx, plus the partial at y times dy, plus the partial at z dz. But otherwise, these are pretty much the same. So let's see an example. I've got f of x comma y is 9x cubed minus 8x squared y plus 4y cubed. So to find dz, let's start by finding our 2 partials. So the partial at x is going to be 27x squared plus 16xy, and the partial at y is going to be negative 8x squared plus 12y squared. So dz, this total differential, is going to be f of x, or the partial at x, I should say. Now, I don't know what dx is, so right now I'm just going to write dx plus the partial at y. And once again, I don't know what that dy is, so I'm just going to write it as dy. And this is, in general, my total differential. Now, most of our problems, we will also be given values, so let's go ahead and do all of that for that particular function. So x is 1, y is 3, my dx is 0.01, x again is 1, y is 3, and dy is negative 0.02. Generally, that dx and dy are going to be small values. They could be either positive or negative, but again, they will generally be small. And at that point, I'm just going to throw that into my calculator and see what I get out. And I get out negative 1.25. So that is the first type of problem we will find, is we will find these total differentials. We may not always be asked for this. We'll usually just jump straight into when we plug in the values, but I did want to write that general term for you as well. Let's do an application type problem with a total differential. So here we've got a blood vessel, which is in the shape of a right cylinder. The height is 42 plus or minus 0.9. Basically, there's an error. It's not a perfect cylinder. It has variability in there. And similarly for the radius, it's 2.5 and with a maximum error, so plus or minus 0.2. And then given that, what is the possible maximum error with the volume? Now, real quick here, if I asked you on a test for anything with the volume of the cylinder, I would give you this equation. I do not expect you to know that. It is pi r squared h. So that is our equation here. So let's go ahead and do our 2 partials. So let's do the partial at both radius and at height. So I'm going to do VR and then VH like that. So here I will get 2 pi h, and then at h, that will give me pi r squared. So then my total differential, which I'm just going to call dV, is going to be 2 pi h times dr plus pi r squared times dh. So then actually plugging these in, well, my height is going to be 42, and then d height is going to be that maximum error. And similarly, my radius is going to be 2.5, and the d radius is going to be 0.2. Oops, I'm sorry, the dh is just 0.9. I apologize for that. So I've got 2 pi, my height is 42, my dr is 0.2, plus pi times my radius is 2.5, which is squared, and my dh is 0.9. And once again, let's go ahead and plug that into my calculator. So 2 times pi times 42 times 0.2 plus pi times 2.5 squared times 0.9, and I get out approximately 70.45. And this is going to be cubic millimeters, because it is volume that we're talking about. So, even though I had an application, the way I set up my total differential was pretty much exactly the same. So that is a total differential. The next thing we'd like to look at is how to do an approximation. This is how we used to find values when the numbers weren't good, before we had calculators. And we're going to use that total differential to do this. So to do this approximation, here's the formula I'm going to focus in on, is we're going to take this function at a particular value, and then we're going to add the total differential dz. And you'll notice I did go ahead and write out what that dz is as well if we want to remember it. Now, compare that to my question. I don't even have a function. So that is the first thing we're going to have to figure out for these problems, is what is a function that we can use to represent this. Now here, you will not need to have 3 variables. We'll need to have just 2 variables, and those will generally be the nasty numbers. So I'm going to write this as the square root of x squared plus y squared. That's my function. The other hard part then is I need to have both an x value and a dx, similarly for y. So I don't just want to plug in x is 2.98. The whole point of this is to plug in nice values. So what we're going to do is each of these numbers should be pretty close to a nice number. So 2.98, well, that's pretty close to 3. The dx then should be a small number, and it's basically the difference between the value I just picked for x and the value I'm actually given. Now, since this is smaller, it is going to be negative 0.2. So similarly for y, 4.01, well, that's pretty close to 4. And again, dy then is the difference between them, which is 0.01. I need a 0 in there as well. So again, your x and y should be nice numbers. Your dx and your dy should be small numbers. If it's not working out like that, then I've probably picked the wrong things. All right, let me do a quick rewrite here. Let's rewrite that as to a 1/2 power, because now I'm going to have to find my 2 partial derivatives. So here I'm going to need a power rule. So 1/2, I leave the inside the same, subtract 1 on the exponent, and the derivative of the inside, where x is my variable, is 2x. And I can simplify that and rewrite that as x over the square root of x squared plus y squared. My partial at y is going to work out pretty similarly. And once again, I can simplify that pretty nicely. All right, so I find my function. I find my x and y and dx and dy values. Now I've found my 2 partial derivatives. So now you can either find the dz separately or go ahead and jump straight into the approximation. I'm going to hit that dz separately. So the dz, that is my total approximation. So again, that's going to be my partial at x times dx plus the partial at y times dy. And let's go ahead and start plugging in values. So my x is 3, my y is 4, here my dx, I'm just going to pop that in the numerator as well, is negative 0.02. My y is 4, and let's put that dy up in there right away, and we will get the exact same denominator. Now, one way to double check that these are going to work out is the whole point of this approximation was it's something that we can theoretically do without a calculator. Now, I'm going to use a calculator anyway, because I'm extremely lazy and I'm used to using a calculator. But these are things that we should be able to do without. So for example, in this denominator, I'm going to get 9 plus 16, which is 25, and that square root is 5. It's a nice number. With the decimals, it gets a little bit nastier, and we may not want to do it by hand, but it is at least something we could do by hand. If I'm getting nasty values that I can't work by hand, then chances are my setup had an issue. Alright, so again, since I am lazy, I am just going to type that into my calculator. And I get out that my total approximation, the DZ, is negative 0.004. Now be careful, I'm not actually done yet. My final problem here was to approximate this. And again, we said the way to approximate that is to take the actual function value and then add that DZ. And let's scooch that up a little bit so you can actually see what I'm doing. So my function, I had the square root of x squared plus y squared. So the square root, again, I'm using my nice values in here. And then we're going to add that value that I just found. So we already did that. It was 5. And so I get 4.996 as my answer. Now, I'm going to do one last step to check. Since I do have a calculator, let's type that into my calculator. So let's do the square root of 2.98 squared plus 4.01 squared. And just to pull this up real quick so you can see, my answer is not quite 4.996, but that's actually pretty darn close. And that is something that we could have done without a calculator, which is the point of this approximation. Now, a lot of the homework will ask us to find that calculator, and even if it doesn't, I will encourage you to do that because that's a great way to check your answer. If the calculator value is totally different than the value I just got by hand, I've definitely made a mistake somewhere. But these are the last few problems that we will have to do where we will need to do one of these approximations. And that is everything in section 9.5.